right, so we're going to start looking at chapter 9, and we're also going to be doing a few new things on the calculator that we haven't done. So we can adjust certain things in the calculator depending on what we're trying to do. So sometimes we change between degrees and radians. Okay, that's a setting that we've done. There's a setting in the calculator for real and complex numbers. Okay, we've done a little bit with complex numbers. There's some other settings we haven't looked at yet. It says function, parametric, and polar. So everything that we've done all year has been in function mode, which means when you type something into the calculator, it assumes what you're trying to graph is a function, meaning for every input value, there is exactly one output value. Right? It passes the vertical line test. We're going to look at some different kind of graphs we can do in parametric and polar this week. Okay? So we don't get into a lot of different things we can do, but we do a little bit. Mostly the graphing will be on the calculator, but there will be a few things that are not graphing we do by hand. Okay, I want to show you just some different graphs you can do in parametric and polar. Okay, if you notice these graphs, for every input, there definitely is more than one output value because it fails the vertical line test. But that's a type of graph we could do in either parametric or polar. Anything you can really do in parametric, you can do in polar, for the most part. Those first two, well, especially the middle one, that's probably a little bit more complicated than what we're going to get into. But with the one on the right, that's definitely one we would look at. It's all just different kind of examples of graphs you can do in parametric and polar. Let me put the calculator in parametric and go to y equals. And you notice it looks a lot different. Right? When we start graphing things parametrically, it's kind of like we're separating the x values from the y values, and we're using two different formulas. Okay? So we're used to just using one formula to graph everything. Well, this is going to give you one formula to calculate the x values, and a different formula to calculate the y values. So an example of something would be like this. That is a pair of parametric equations. Okay? Top formula, plug in a number for t, and it'll calculate the x. The bottom number, plug in something for t, and it'll calculate the y. So it's two different formulas. We're going to call each of those formulas in this particular definition, f and g. So function f is a formula that I would give you that's going to calculate the x values. And function g, that's another formula I would give you, and that will calculate the y values. The other thing you'll notice about the two formulas is we're using the letter t. Usually the letter that we plug in for, we call x. That's our independent variable. Well, the independent variable here is going to be called t. And when you're doing things parametrically, if you put it in parametric mode and you press the button that used to give you an x, it's now going to give you a t. So that's like your variable that you're plugging in for. It's t. And generally, we call all the graphs that we're doing parametrically, at least our book calls them this, curves. They're all parametric curves. Whether or not they're really curved, that's not really how they're using the word curve here. They're just using the word curve to mean a picture of a parametric equation. That's all. Could be a straight line, could be a spiral, could be all kinds of things. Now, notice I also mentioned something about an interval. Okay. You kind of think of the interval as like the domain for t, right? It's a set of values that you are allowed to plug in, and they have to tell you that. Right? So for this particular problem, they're telling you the numbers you're allowed to plug in for t in the top two formulas are between 0 and 1. And it's not because if you go outside of 0 to 1 that you get an error. There's no square roots in this problem. There's no variables in the bottom of the fraction. So you could plug in, technically, anything for t, and it would work. But what they're telling you is they don't want you to do that. They only want you to plug in values between 0 and 1. And that's called your interval, or the domain of t. Every parametric problem has to have an interval with it. Okay, if I don't give you an interval, then I guess you just assume the interval is all real numbers, right? So every parametric problem has an interval. Usually I'm going to tell you what it is, and it's usually not all real numbers. So the two equations that I give you when you're graphing something parametrically, those are called parametric equations, and they always come in pairs. I can't just give you one. That would be like me giving you a coordinate and saying graph that coordinate, 3 comma nothing. Well, you can't. You've got to have a value for the x and a value for the y. Okay, so I'll always give you both formulas. And again, the variable t, that's our input value. What they refer to that as is a parameter. They call that the parameter. It's really just the input variable. Okay, any questions on anything I put on that first page? That's kind of the background in parametric equations. Now, because it's a new type of graphing, it is a little tricky to just look at a pair of parametric equations and know what it's going to look like. There's lots of graphs you should be able to look at and know. Like if you graph something like that, or the basic kind of graphs we've done all year. These things, we know what they look like. All right? But parametric, it's kind of brand new, so we don't really know, looking at it, what it's going to look like. So we're going to use the calculator to help us out a little bit. Okay, and when you have a graph and you find two equations that model it, we've basically done what's called parameterize the graph. Parameterize means you've taken the graph and you've written it parametrically. Because there's lots of types of graphs we can write many ways. We can take a parabola, and I can show you how to do it as a function, like y equals x squared. I could write it parametrically, or I could also write it in another system we'll talk about later on, which is polar. Okay, so some graphs can be written all three ways we're going to study. Some graphs can't, all right? Like something like a spiral. I can't really do a spiral using function notation, because the spiral is not a function. But I can do a spiral parametrically, and I could do a spiral in polar. Okay. We've already seen some examples. Curves can intersect themselves. Not something we're used to seeing when we graph as functions, because that can't happen. But the curves can cross over themselves as you're drawing them. One thing that will help us to try to figure out what a graph looks like is finding the start point and the end point. Unless your value for t is all real numbers, then every parametric graph has a start point and an end point. So let's say they give us an interval. Okay, these are the numbers that you would be allowed to plug into your formula. In the example we're going to do, it's going to be every number from 0 to 1. But in this example, it's every number from A to B. This value, the lower value in your interval, that controls the start point. I'm not saying it is the start point. I'm saying it controls where the start point will be. And B, that's going to control the stop point or the end point. So So the way that you use the A and the B to figure out where the graph starts and where it stops is you take the A value, and the first thing you're going to do is you're going to plug it into the formula that gives you the x's, and then you're going to take the A value and plug it again into the formula that gives you the y's. And that's going to tell you where the graph starts. To find where the graph stops, you're going to take the B value, and you're going to fill that into the formula for the x's. And then you're going to take the B value again and fill it into the formula for the y's. So there's 4 calculations you need to do to figure out the start point and the end point. Now, just knowing where a graph starts and stops, does that tell us what it's going to look like? No. Is it a line segment? That'd be the simplest thing between the 2 points. Or is it something that goes like that? We don't know. Okay. Just because we know the start point and the stop point, we don't even know if the start point and the stop point is the highest and lowest that it ever goes. Okay. In our case, that's the level of the start point. That's the level of the stop point. It didn't even stay between the 2 y values as we drew it. It actually ended up going a little bit lower than the start point and a little bit higher. Right? So just knowing the start and the stop isn't enough, but it can be helpful. So let's try to see if we can figure out the start point and the stop point for this particular graph. Okay, so I've given you a pair of parametric equations. The formula for x is 1 minus 2t, and the formula for y is 2 minus t. Okay, the values that you are allowed to fill in for t are any values between 0 and 1, all real numbers, fractions, decimals, everything between 0 and 1. Okay, so which value in my interval is going to control where the graph starts? So which number there? So no, the 1 is going to control where the graph stops. So that number controls the stop point. So the number that controls where it starts is the first value, which in this case is 0. All right. So Jaden, how would I figure out where this graph is going to start, knowing that this number is what is going to help us to control where it starts?
Do you like plug it in?
Yep. What are we going to plug it into?
To xt?
Yep, x of t, and
I'm not sure.
all right, well then let's start with that. All right, so how would you, what's the x of t formula?
Oh, is it 1 minus 2t?
1 minus 2t. So we're going to plug in 0. That controls where the graph is going to start. And we're going to get 1 minus 2 times 0. Which is how much? 1. Okay, so now we're trying to find the coordinate of where the graph starts. We know it starts at an x value of 1, but what else do we need to know? We need to know the y value. So we're going to plug the same number into y, and that'll tell us where the y value of the start point is. Okay, so 2 minus 1. So 2 minus 1 gives us 1. Now we know that this particular graph is going to start at the point 1, 1. All right. Now we're going to figure out where it stops. What number do we plug in for t to figure out where the graph is going to stop? How about Annalise? What number would you plug in? The 1. So we're going to plug in. What are you going to plug it into? Wait, did I make a mistake?
Yeah.
Let's see. 2 minus, oh, this should be a 0, right? Thank you. Yeah. So sorry, we're plugging in 0. So that should have been a 0, and that makes that a 2. Sorry. Thank you. All right, so yeah, you said we're going to plug in the 1, and what formula do we plug it into? Yep, the x and the y. So we're plugging the lowest value of our interval and the highest value of our interval into both the x and the y. So the top one, we've got 1 minus 2 times 1. We're filling in 1 for t. And the bottom one, we've got, this is what I was thinking of when we did the top one. It's going to be 2 minus 1. So at the top, we're going to get 1 minus 2. In the bottom, 2 minus 1. And those are the x and the y value of the stop point, or the end point. Negative 1, 1. Okay. So let's draw that. Okay, I'm going to show you how it looks. But before we do it, I want to think of something that you probably don't really look at very closely when you use the calculator, but something that always happens this way. When you put something in y equals and you hit graph, what direction does it draw the graph in on the screen? Yeah. It always goes from left to right. Okay. Every time we draw a graph in y equals, it always starts at the left edge of the screen and it draws it towards the right. What's going to happen here? Think about if you start at the point 1, 2, and then you travel to negative 1, 1. What direction are you traveling in? Specifically on like the x-axis. Yeah.
Right to left.
You're going from right to left. You're going from 1 to negative 1. So when you if you watch the graph as it does it quickly, you'll notice it is going to draw right to left. It's not going to draw left to right. And that will always be the case. It will always draw from the start point to the end point, whatever direction that happens to be. Okay. Any question on that? All right, so let's put this in. So for x, you're going to put in 1 minus 2t. So press the button that you normally would use for x. That'll give you a t. And then the y value is 2 minus t. Now, just like graphing when we do it in function mode, we do want to set the window. Okay, I'm going to set everything, I think negative 3 to 3 will fit everything that we need to see. So the T-min and the T-max, that's given to us in the problem. The lowest value you can plug in for T is 0. The highest value you can plug in is 1. So that's something new you need to set when you graph it. You have to put in the T-min and the T-max. That's the interval of your parameter. T-step is pretty important, but we're going to just leave it at 0.1 right now. I'll explain what that is in a minute. For x-min, again, negative 3 to 3, I think will give us a good window. So let's hit graph, and if you watch it quickly, it should draw from right to left. And it did, if you saw it. It went right to left. Okay. That's what our graph looks like. This one is a line segment. It's a very simple parametric graph. It's just a line segment. All right, so what does that t-step do? Well, the t-step is basically controlling how many points the calculator is going to graph between the starting point and the ending point. Because that's all the calculator can really do, is just draw a bunch of points and then connect them all with straight lines. If you do a t-step of 0.1, okay, what's going to happen is if your interval is going from 0 to 1, the calculator is going to plug in every number from 0 to 1 in the x formula and the y formula, and it's going to step or increment by 0.1. So the first number it'll plug in is 0. Next one will be 0.1, 0.2, 0.3, 0.8, 0.9, and 1. So it's going to end up plugging in all those numbers from 0 to 1 going by tenths. Right? So now, if I go 0.01, what's going to happen is the calculator is going to plot every single point from 0 to 1, incrementing by hundredths. So that's going to give you over 100 different points in that line segment. What do you think is going to happen when I hit graph if I make the calculator evaluate a lot more points? Yeah?
Maybe the graph would look a lot more straighter.
Okay, so sometimes we get a little bit more detail. We can see, especially when things start to curve, if you don't plot enough points, things that are supposed to look circular might end up looking a little blocky. But we're just doing a line segment. So we're not going to really see that much more detail. But what else do you think is going to happen? Yeah?
Just like graph it slower.
It's going to be slower. It's going to graph it 10 times slower because now you're making it graph 10 times as many points. You can see that was a lot slower. Now, if I go in thousandths, now we're graphing 100 times slower than the original. Okay, that's going to take a little bit of time to graph. Right, it'll do it, but it's graphing every single number from 0 to 1, incrementing by thousandths. So it's graphing over 1,000 points to get from the beginning to the end. That's way too much detail for a line segment. You don't need that many points. Okay? Even something that's curved, we probably don't need 1,000 points. Right? So when you're drawing it, if you accidentally put in a t-step that's too small, that's, did I mess up the t-step? Oh, I guess I can't handle that. So that's going to take too long. Okay, it's probably going to take at least 3 minutes, maybe 2 or 3 minutes. As long as this yellow circle is spinning, it didn't freeze and it's still doing something. I can stop it by pressing second off, and now I can fix it. Right? If you don't press second off, you can't touch any other buttons on the calculator, it won't respond. But now the yellow circle's gone, I can go in and change my t-step, and I'll be all set. Now, let's say you did a t-step of 0.4. If you start at 0, the first point you're going to get is 0. What would be the next value that it would plug into the formulas if you increment by 0.4? Yeah, 0.4. What would be the next value that it would do after 0.4? Yep, we do 0.8. And what would be the next value? Yeah, there isn't one. Now we have a little bit of a problem. We're supposed to end at 1. Okay, that's the interval for my parameter. The next one would be 1.2, but it can't do that. So what's going to happen is the graph is not going to be complete. Right? It's going to show what it can, but that's not what it looked like originally. That line segment going down and to the left was a little bit longer, but you picked a t-step that was not good. Right? We generally want to pick a t-step that if you count by that step, you can end at the number they give you right there. So tenths was fine. Okay? And if I put it back on a tenth, you'll see that the graph is actually a little bit longer, and it cut it off in that other one. Okay? So that's just something we have to be careful about. Now, if the graph is ending like within 1/100th of where it's supposed to, it's probably going to be fine. But this one was ending 2/10 away from where it should have. That wasn't a great picture. Okay. Any question on that one? So sometimes what we can do is we can take a problem that is written parametrically and we can convert it back to what we're used to graphing in, okay, a function. When you do that, that is called eliminating the parameter. And you're converting it back to like a y equals, you know, it could be mx plus b or something like that. But you're converting it back to what we're used to. So let's take that first example and see if we can eliminate the parameter. Okay, so there's the two equations that we started with. The formula for x is on the left, the formula for y is on the right. And does anyone have an idea of how we could eliminate the parameter? So when you're done, you have a formula that's y equals, but it has to be in terms of x. It can't be y equals with a t. So somehow I got to take both those equations and put them together. Yeah?
You could rearrange the equation for x so that t is isolated. So then
Okay.
you could substitute that equation for t in the y equation.
Yep, exactly. So we're going to isolate the t in the x equation. So when I do that, I'm going to subtract the 1. And now I'm going to divide everything by -2. And I'm going to do that and write things as fractions. So I'm going to have -1/2 x plus 1/2 equals t. Yeah, you could leave the whole thing over -2, but the problem is in the next step, I'm going to want to combine like terms. It's easier to write it like that. Okay. Any questions how we solve that for t? All right, so now you're going to take that and fill it in. So you get y equals 2 minus -1/2 x plus 1/2. What would I get when I distribute that and combine like terms? Raj? 1/2 x plus 3/2. Yeah, so we get 1/2 x. And then when we distribute, we have 2 minus 1/2, which is 3/2, or 1.5. Or as you said, I think you said it is 3/2, right? Yeah, that's fine. Okay, so we just eliminated the parameter and converted a pair of parametric equations back into a function. Now let's graph that and see if it looks. All right, let me save our graph first. So that is the parametric. Let's graph 1/2 x plus 3/2 and see if it looks just like that. Okay, so go back to your function. The nice thing when you change between modes, the window stays the same. So we set everything from -3 to 3. That will carry over no matter what mode you're in. So you've got 0.5. I'm just going to do a decimal because it's easier. 0.5x. Plus 1.5, okay, graph. And let's compare that. No. Well, just compare them on the screen right there. Do those two graphs look the same? Yeah?
Yes, they just don't have the stop and start.
Okay, it needs to have the start and the stop point. Okay, we can't, those two graphs are not identical. Right? The section here does match up with a section on this one, but we have to make sure that the going beyond those endpoints doesn't happen. So what do we have to do with this graph to indicate we don't want it to go on forever? do you think we have to do? Yep.
You have to set the x and the x value.
Right, we have to put a restriction on the domain. So we have to say, yep, that's what we want to graph, but we only want to graph it starting at a certain value and stopping at a certain value. Well, we already know where we want it to start and where we want it to stop. When we put a restriction on the domain, all we have to do is restrict the x, the numbers we're allowed to plug in. So on this particular graph, just tell me that you want to restrict the x value to be between -1 and 1. And then you'll automatically get the correct picture. Right, so let's try putting in that restriction. Remember, when you want to put in a restriction, you need it in parentheses. Okay, so you take your graph, put it in parentheses, and then put the restriction you want next to it, but you can't type it in as a compound inequality. So I have to type two separate restrictions. I'm going to allow x to be any number above -1, but I'm also going to say it has to be below +1. So x, second math, has to be greater than or equal to -1. And then I'll put the next restriction, less than or equal to +1. Let's hit graph now. There's nothing I can do about having it draw on the x-axis. I can't fix that. That's as good as I can get. So let's compare that to that. And now, minus the part that's drawn on the x-axis that I can't fix, they look identical. I'm actually comparing it to the one down here. Okay, so that's part of eliminating the parameter, not only finding the formula that you want to graph, but also telling me the domain over which you need to graph it. Okay. When I write the domain on paper, I do it as a conjunction, but I can't type it in that way on the calculator. It just doesn't work. You can try it. Maybe it works now, but I don't know. Last time I tried it, it didn't work. Any questions on that one? All right. Let's try this one. Eliminate the parameter. Okay. So what's the first thing I would do to eliminate the parameter on this one? Isolate t in the x equation. Yep. And what would t equal?
T would just equal x plus 1.
T would equal x plus 1. Yep. Perfect. So that's step one. Isolate the t. What's the next step? Yep, Jackson.
Plug the value into the y equation.
Yep. Take that value. I'm going to plug that into the y equation for what letter?
T.
T. That goes right there. Okay, so let's do that. We get y equals x plus 1 squared. We can leave it factored. There's no reason to FOIL it out unless they told us to. So that is our equation. It's a parabola that's been shifted 1 unit to the, which way has that been shifted? Yep. Left 1 unit. Yep. Bless you. All right. So now, if I were to graph that, and I were to graph the parametric problem they gave me, would the two graphs look identical right now? Travis, what else do I still need to do?
The restrictions.
I need to put in the restriction. Yep. There's going to be a start and a stop. And I haven't used this yet. That's how I need to figure those out. The restriction is always on the x variable. You never restrict, when you're describing an equation, you don't restrict the range, you restrict the input, the domain. So we have to look at these two numbers and plug them in for x. And just because you're plugging in this one first and this one second, that doesn't guarantee this one, when you plug it in, is going to be smaller than that one when you plug it in. I don't know what's going to happen, but I'm going to plug both numbers in, and I'm going to put the smaller number on the left, and I'll put the bigger number on the right. All right, so let's try plugging in 0. When we plug in 0, we get -1. Let's plug in 3. Plug in 3. 3 minus 1 gives me 2. So that means this particular graph, we're going to draw it from -1 to 2. Okay, let's try it and see how it looks. All right, so we've got, what was it, x minus 1 originally? T minus 1. Let's do it in parametric. Okay, so I got t minus 1. I've got t squared. Okay, interval for my parameter is 0 to 3. That's fine, stepping in increments of a tenth to go from 0 to 3. You're going to get about 30 something points. That's fine. Tick graph. Okay, window. Probably need to go a little higher on the y max. Let's try 5. Wait, what's the highest it's going to go? 3 squared is 9. Okay, so let's go to 10. So that is what your graph should look like. It's part of a parabola that's been shifted left 1 unit. Let's try our formula and see if it matches up. Okay, so go back to function. Put in y equals x plus 1 squared. Set your window. Oh yeah, it carries over, so we shouldn't have to set that. We just have to put in our restrictions, which put this in parentheses. And then we need x to be greater than -1, greater than or equal. Greater or equal to -1. And we need it to be smaller than 2. Second test. 6, 2. Let's see what we get. Again, I can't fix the part on the x-axis. I guess what I could do is just kind of cheat and cover it up, but it's as good as I can do. Right, but that's what your graph should look like, and that looks perfect. Okay, any question on that? All right, so again, what we just did was eliminating the parameter. That's not always possible to do. Okay, sometimes you have equations that, yeah, it's not easy to do that with. Right? But if I ask you to eliminate the parameter, it will be a problem that is doable. But what I want to do now is reverse it. Okay? I want to take something that is not parametric and make it parametric. That's always doable. You can always write something parametrically. So there's one more sentence here I have to write down, but I want to show you the next problem and see if somebody can figure out how we could write this parametrically in the simplest way possible. Okay, so leave room for, there's one more line, but that's it. But I want to show you the problem first and see if you can figure it out. Okay, so there's your problem. It's written as a function, y equals 3x to the 4th plus 7x cubed minus 8x squared plus 2. And I want to see if I can write it parametrically. Now, first thing is they don't tell us any restriction on the x, which means x is all real numbers. So when you write this parametrically, your interval for t min and t max would be all real numbers. Now, realistically, you can't plug in a negative infinity and an infinity symbol for the t min and t max. So I just plug in big numbers like negative 50 to 50, just to get an idea of what it's going to look like on the screen. Okay. Anyone think they could come up with a really simple way to write this parametrically? So try to think like we were doing it backwards. First thing you do is you solve the x equation for t, right? And then you plug it in. Well, what could we write down that would be a really, really simple equation for the x formula? Looking for something that's really, really simple that I could then solve for t. So the x equation has to have a t in it. But it has to be, I wanted something very, very simple. Yep.
Could x equal t?
Okay, so let's try x equals t. And if you did that, what would be your formula for y? That now you could substitute that in, and it would give you back what you started with.
Y equals 3 t to the 4th power plus 7t cubed is 8t squared plus 2.
Yeah, it's kind of a cheap way to do it, but it works. That technically, that is parametric. All you've done is make x equal t. So now if you were going to change this back to a function, I would say, okay, solve the x equation for t. Well, it's done. And then plug in, everywhere that you have a t in the y equation, plug in what t equals. Well, t equals x. So you just change all the t's back to x's, and you'd be back to what you started with. So, yeah. You can always do that if you want to make something parametric. Is that the only way you could make it parametric? No. You could come up with other ways. But that's the simplest way. Feels kind of cheap, but it works. Any question on that? Okay. All right, let's look at starting to graph something that's now curved. Okay, we're going to find the equation of a circle. So to think about a circle, don't even think about the entire circle. Just think about one point on the circle. Okay, we're going to do a circle that's at the origin, but I could shift the circle left, right, up, or down very easily. Let's start with this point. Right, actually, you know what? Let me do it so it's going to be easier to draw. There's a point. If I wanted to find the coordinates of that point, what shape would I try to create here? Yeah, a triangle, right? I would draw in a hypotenuse, and then draw in the two legs, base, height. This is your x value. This is your y value. If you could tell me the length of the base of the triangle and the height of the triangle, then you've just told me the coordinates of this point. And now, if you can do that for any point, or every point on the circle, every point has an x and a y value, and we can find them all using the formulas that we're about to come up with to find just this particular point. Okay, the formulas are going to work for every point on the entire circle. What would have to change in this triangle for this point to start moving around the circle. What is it in that triangle that really controls that point being right there? Yeah?
Would be the y value.
I'm thinking of something else besides like side lengths. Yeah? Well, that's always going to be a 90. That'll never change. No matter where you put this point, it's always going to be a 90 right here.
Or would it be
The angle, right? This angle right here, we can think of that as what controls where on the circle this point is going to be. That's our angle of a rotation right here inside that triangle. Now, what do we normally call an angle that we don't know? How do we represent it? Yeah. Yeah, we use a Greek letter, we use theta, but we're doing it parametrically. So what letter do you think we're going to use to represent this angle? Yep.
T.
T. As t changes, you will change the position of the point on the circle. We just have to figure out the coordinate, or how to figure out the base and the height. Okay. Now, I don't know the radius of this circle. Could be any radius I want. Let's just call it r. What trig function would I use that would involve x, t, and r? Lens?
Would be like cosine t.
Yep. And what would your formula be? Cosine t equals,
Cosine t equals x.
and solving for x,
Basically, would be r cosine t.
r cosine t. And could someone give me what the formula would be for y? Yeah.
R sine t.
R sine t. So now you have a formula that calculates the x value of the coordinate. You have a formula that calculates the y value. You have a pair of parametric equations. Those are the two equations that you could fill in for x and for y to draw a circle. Change r to how big you want the circle to be. And t is your perimeter. So let's try drawing a circle specifically with a radius of 2. So now I don't want to write r, I want to fill in what r would be in that problem. So Marin, what would be the formula for x to draw a circle with a radius of 2?
Or the radius is so 2 cosine.
2 cosine t. So we're going to fill that in for x. And what would be the formula for the y value of the coordinate with a circle of radius 2? Yep. 2 sine t. So let's type that in and see what we've got. Okay, I'm going to do it in degrees. And since we're dealing with sine and cosine, that makes a difference. Okay, so pay attention to your mode. Okay, so we're going to go into degrees and we're going to do it parametrically. We're going to do 2 cosine t, and we're going to do 2 sine t. Okay, let's think about our window. We're drawing a circle of radius 2. Now the screen is rectangular, it's not square. So if you set the window to go -3 to 3 and -3 to 3, that'll work. The circle will fit, but it's going to look like an ellipse because you're fitting in -3 to 3 horizontally and -3 to 3 vertically. So it's the same amount of units, but it's over a different size space because the screen is not square. So it won't look circular, but it'll draw okay. Now, T min and T max, we're in degrees, and we want to get a full circle. What do you think my T max would have to be for me to draw the full circle? This angle has to go through every possible value that it can to make sure that that point hits every location that it's supposed to hit to make a circle. Yeah.
360.
It has to go to 360. Yep. So 360. Now, incrementing by 0.1, that's a little much. That's over 3,600 points. I would think even if we go by like 5s, that's fine. Counting by 5s all the way to 360, that's going to give you, well, if you counted by 10s, that'd be like roughly 36 points. If you count by 5s, that's like 70-something points. That's pretty good detail. So hit graph. Oh, I thought I was -3 to 3. Okay, I wasn't. Let's do zoom 6. So you can see it is a circle, because if you count the tick marks, it's going 2 units in every direction. But if you want it to look circular, you can press press zoom and press square. And what that'll do is it'll make things look, well, it didn't drag over, but it makes it look more circular. Now let me zoom in, see if I can just make it a little bit bigger. Yeah, that's good. What would happen if I go by 20s for my T-step? What do you think is going to happen to my picture? Yep. It's going to draw faster, and what's going to happen to the picture? Yeah.
Might be a little less circular.
It's probably going to look a little less circular, a little bit more like a, well, not too bad, but I can definitely see it's a little more jagged. Bottom actually looks a little bit flatter. If I want to really exaggerate it, let's go by 40s. Okay, now we're starting to see it doesn't look circular. Okay? Because when you go by 40s, what the calculator is going to do is essentially it's plotting a point every 40 degrees. So 0, 40, 80, 120, and so on. And then it's going to connect all those points. Okay, so it doesn't look circular. What would I get if I went by 90s? What would this shape look like? If it plotted a point every 90 degrees and then connected all of them. Yep.
Square.
Yeah, it's going to look more like a square. Which, if that's what you're trying to draw, great. But we were trying to draw a circle, so we need a little more detail. Okay. But it's plotting a point every 90 degrees, and then it's just saying, okay, I'll connect all the points. Okay, so I think, for our purposes, one of the first ones we had, that was pretty good, going by 10s. That's great. That looks good. Now, if you go by, let's say you go by something that's not a nice number, it doesn't land you at a nice spot. Let's go by 50s. Okay. The problem you're going to run into is now when you count by 50s, you're going to get 200, 250, 300, 350, and then the next one will be 400. So now you're going to have a gap, and the shape isn't going to close at the end. Not only does it doesn't look circular, but we want to avoid that gap. So try to pick a T-step that counts into your T-max. Okay. And if you want to shift left and right, well, it's actually easier than what we're used to because we have separate equations. If I want to shift left or right, I add or subtract a number to the x value. I just shifted my circle 2 units right. If I want to shift my circle up or down, I can add or subtract a number to the y value. Okay, so the transformations work a little different. They're separate. Okay? Adding or subtracting to x will shift it left and right. Adding or subtracting to y will shift it up and down, and it's not backwards. Adding will shift it right, subtracting will shift it left, because we're breaking it apart and doing it parametrically. But if you don't add or subtract, it's going to keep the circle centered right at the origin. Any questions on that one? So notice when we did the circle, the domain for the circle was -2 to 2, and the range was -2 to 2. That's where the circle fit on the screen. But the domain for the parameter was 0 to 360. Gets a little tricky when you do it in radians because you're going 0 to 2 pi. So 2 pi is not a nice number. So it's going to be hard to find a t-step that lands at 6.28. If you go by 0.05, that's probably going to be close enough because you're counting from 0 to 6.28, and if you go by 0.05, the gap is going to be so small you probably won't see it. All right, let's try a few more graphs. So here's two equations. Before we graph it, it helps to kind of think about it a little bit, because if we don't know what's going to happen, we're not going to be able to set our window. So we kind of need to analyze it before we can jump into the calculator. Think about cosine t. When you plug a number in for t, what's the range of cosine always between? Just basic cosine. What's the range on the graph of cosine? Yeah. -1 to 1. Now, this is always going to be between -1 to 1. And it's going to be being multiplied by a value between 0 and 4 pi. So if everything lined up just right, what is the smallest value you could ever get if you take something that's between -1 and 1 and multiply it by a number between 0 and 4 pi? What is the smallest value you would ever get? Yeah? Well, it's going to be something with pi. It has to be something with pi. Yeah? -4 pi. If everything lined up just right, and this was -1, and this was 4 pi, -1 times 4 pi is -4 pi. What would be the largest value you could get if you multiply a number between -1 and 1 by a number from 0 to 4 pi? If everything lined up just right, and this came out to +1, and this came out to 4 pi, 1 times 4 pi is 4 pi. And the same thing happens on t sine t. So that gives me an idea of my x min max, y min max. I'm going to go -4 pi to 4 pi on each. So let's set the window. -4 pi to 4 pi. And that's like worst case scenario. That's the most it could ever do. It might not even do that much if the things don't line up right. -4 pi and 4 pi. Now my t-step, do they give me a t-step? Yep, 0 to 4 pi. Okay, now what would be a good value to go by for the t-step? I would say 0.1. If I count by 0.1, am I going to land at 12.56? No. I'm going to land at 12.5. And then the next value that it would try is 12.6, but that's beyond the end of the parameter. So 0.1 is going to leave a little bit of a gap that's it's less than 1/10. So it's not bad. Okay, and we're going to plug in t cosine t, t cosine t, and t sine t. Now, kind of looks like the equation of a circle. X is a number cosine t, y is a number sine t. The difference is what's in front here is not a number, it's a constantly changing number. So what kind of shape do you get if you try to graph something that looks like a circle, but the radius is constantly changing? What shape would that be? Yep,
Spiral.
it would be a spiral. Specifically, you're going to get 2 revolutions of a spiral, 0 to 4 pi. Okay? Why doesn't that look right? What do I have to fix? Yep.
You have to put it into radians.
I have to be in radians because I'm using sine and cosine, and they gave me values with pi, not degrees. So put it in radians. There's 1 revolution of your spiral. There's 2. And the only direction that I really needed that maximum amount of room was on the positive x-axis. I could have made the other ones a little smaller. And there's a very, very, very small gap. I think it's like 2 pixels. And that's, if I wanted to make it a little better, I could make the t-step like 0.05. And it would be a little better, but it would take twice as long to draw. And those curves, they look pretty smooth. They're not that jagged. Okay. Any question on that one? So that's a spiral. Let's try this one. So 2 equations. So what I like to do is just try to analyze it first. Sine is always between what? What's the range of sine? Layla, what's the range of sine? So when you graph sine, what's the highest and the lowest that the graph of sine goes? Negative 1 to 1. And what if you multiply that by 5? Yeah. So this graph, this part, on the x-axis is always going to be trapped between negative 5 and 5. But let's look at this part. Cosine is always between negative 1 and 1. Okay, so this part is between negative 1 and 1. How about this part? 5t. What's the biggest value that you could get there? Or what's the smallest value? What's the biggest? No, t can't get infinitely large because there's a limit on t. T stops at a certain point. Yep.
The smallest might be -5, or the largest would be 5.
So what numbers are you plugging in for t?
0 to 20.5.
0 to 20.5. So if you plug in those numbers for t and multiply them by 5, what's the smallest value you could get? Yep. 0. So the smallest that this part could ever be is 0. What's the biggest that that part could be? 102.5. So if everything lined up just right, the biggest y value you could ever get when you multiply this times that is 102.5. And the smallest y value you could ever get is negative 102.5. So that is what we're going to use for our y min and max, 102.5. So let's go to window. I'm just going to do negative 105. 105, that's fine. X, what did we say? Negative 5 to 5. So negative 5 to 5. So this is a graph that's going to keep growing on the y-axis. The higher I make t, the higher it would keep growing. Okay? The only reason it's not growing forever is because it's limited right there. but it's going to stay the same width, but it's going to constantly keep growing in height. So let's see what that looks like. T step, 0.1 again, that's fine. Let's do 5 sine t and 5t cosine t. Okay, so remember, trapped on the width, constantly growing on the height. So it's pinned on the width between -5 and 5. And I forgot to set my parameter. Tmax is supposed to be 20.5. So it's basically going back and forth, but it's going to continue getting higher and higher. It's kind of like a watermelon or something. I don't know. But that's what that graph looks like. Okay, any question on that one? All right, and the last one. All right, this one has no value for t, so tmin and tmax can be as high or as low as you want. All right, so when I look at the x's, this part is between -1 and 1. When I multiply it by 5, that's going to make this whole part between -5 and 5. So that gives me an idea of what's happening there. But this is unbounded. If you make t 1,000,000, you're going to have 5 million plus or minus 5. Right? If you make this 10 billion, you're going to have 10 billion times 5, 50 billion plus or minus 5. So it's unbounded. Right? So x can go forever. So that makes it a little tough to think about. But y is bounded. This part is between -1 to 1. When I multiply that by 5, I get something between -5 and 5. And now I'm going to take 5 and subtract something between -5 and 5. So the smallest I could ever go is 0. If I had 5 minus 5. And the biggest I could go is 5 minus -5, which would be 10. So I know my y is trapped between 0 and 10, but my x's go forever. All right, so let's try to graph it. So we've got 5t minus 5 sine t, and we've got 5 minus 5 cosine t. Okay, y's are trapped between 0 and 10. Let's go, I don't know, let's try 0 to 40 because they don't give me a Tmax. And x's, I'm just going to try some values and see what it looks like. I'm going to try 0 to 50. All right, let's set the x max bigger. Let's go out to 200. I think we're going to start to see a pattern. So we're trapped on the y. It's not going above and below that. And it's basically this kind of cyclical pattern where it's almost like something that just keeps bouncing. And if I went further to the left, you would see the same thing. How long is it going to bounce for? Well, there was no limit on the t. So that's what the graph looks like. All right. And that's a good picture. That shows what it looks like. So that particular graph that we just did in the last problem, it had that pattern if you look at the two equations. I could factor a 5 out of the top and write it as t minus sine t. And I could also factor a 5 out of the bottom and write it as 1 minus cosine t. That's called a cycloid. So that last particular graph just has a special name. And it's called a cycloid. I didn't put the equations in factored form, but I could have. I could factor the 5 out. And kind of the interesting thing about a cycloid is if you take this and rotate it like that. The curve that you get right here, dropping down, that is the fastest possible curve you could ever have if you wanted a ball that would roll down and hit the bottom in the quickest amount of time. So like if you made a roller coaster in the shape of a cycloid, that would be the fastest way to get from here to here, going down on a track. The curve of a cycloid. You might think, oh, maybe a straight line from the top. No, it's not a straight line. It's a cycloid curve. It's the fastest way to get down. All right, so that's section 9.1. Okay, so homework for tonight. Yeah, that's the homework. So page 481. We'll take a look at that tomorrow. And just reminder, if you are going on that field trip, make sure you talk to me before you go and let me know if you're going to do the test Wednesday or Thursday after school, or if you're going to try to do it Monday or Tuesday during school next week.